Swayam Prabha. Digital India. Educated India.
Okay, so welcome back. Let us look at two examples first, and then I think we'll move on to something interesting. Okay, so let me write this down. So from the empirical laws, for the central line velocity, and the jet half width, show that that's interesting, isn't it? And okay, so this is essentially an example that I'm looking at. Okay, so from the empirical laws, right, we need to show that the rate of change of the central line velocity along x is actually equal to the central line velocity by the x, which is the distance traveled, and the negative sign of that. Okay. And the other is we have an expression. So if we take that, if we take this, the rate of change of central line velocity along x, and multiply that by the jet half width, the ratio of jet half width and the the central line velocity, then what we get is the spreading rate, right? Okay, so let's see if we can do that. Okay, so how are we going to proceed with this? So what is this empirical relationship that we're talking about? So let's just say this is, we're going to have a solution for this. Okay. Now, what is the empirical relationship? This is something that we've done earlier. Okay, so this is so that is essentially central line velocity by the jet velocity. You remember B is a decay constant, right? Or it was like 1 by slope, right, of the plot, okay, of this on the left hand side and what I'm going to write on the denominator. So x minus x naught by diameter, or let's say characteristic length. Okay. So this is my empirical relationship, right? And it is given to us here that x naught is actually equal to 0. Okay, so x naught is actually equal to 0. So using that, then we can write again from here, right? I'm going to write an expression u naught of x is actually equal to b into d into uj by x, right? Okay, since we have x naught is equal to 0. Okay. Now, using this, so then from here, then we will take a derivative. Right, we will take the derivative with respect to, differentiate with respect to x, right, and what we get here. Correct? Yeah. So, if you have that, now we are essentially going to use this relationship again, okay, this relationship, okay, again. So, because you can see that u naught x is equal to b d u j by into 1 by x. So, essentially I am going to use this, right, as 1 by, so I can use an expression for 1 by x squared and we will see what we get. Okay. So, then so or, okay, right, is equal to, so let me write it like this. This is b d u j, right, into 1 by x, right, into minus 1 by x. Makes sense, right? And this is the part which we can get an expression for here. Now, that part is nothing but u naught x, right? So, therefore d u naught by dx is nothing but minus u naught by x. There, that's it. Simple, right? We take the empirical relationship and this is what we get. So, this is the the answer to the first one, right? This is what we were asked to figure out. Okay, that's simple, right? Okay, again the next one we need to show that this, right, now that we have proven this, we have to go and show that. Let's see if we can do that. Okay. Now, again our empirical relationship into this, again x naught is equal to 0. So, we can write x, right, or this, right. But again from 1 by x, we have seen that, right. So, this whole thing, so 1 by x, right, 1 by x is nothing but, or 1 by x is nothing but this expression here, right, is minus 1 by u naught d dx of u naught. This is what we get from here, right. So, or yeah, so this is equal to minus 1 by u naught d dx of u naught, right, which is equal to s by r half into x, right. So, or we just need to arrange that, that's all. So, r half by u naught d dx of u naught is equal to minus s. Okay, so that's it. So essentially, a simple using the two relationships which we have derived earlier. So from that, we use just a very simple working out, so sort of almost rearranging, and we get this, and the next one also is here. Okay. All right. So now another one. Okay, let's look at another example. So approximation to the self-similar velocity profile. Okay. Velocity profile is f of theta okay. Now so basically the point is that what kind of a velocity profile does become self-similar. If you knew that the answer to that question, it would really lighten up our lives, right? So say we have a velocity profile which looks like that, right? So then, and we're saying that this is self-similar. Okay, we have this constant here a. So show that a is equal to root 2 minus 1 by s square, right? From the definition of r half. Okay, so let us see how we will proceed to that. Okay, now eta is okay, and f of theta is equal to the mean value by the central line velocity, right? So that is eta and f theta. Now by definition, r half right. So r half by x minus x naught, right, is equal to s, right. So which is the spreading rate, right. Now if you look at the eta, right, r by x minus x 0, okay. So essentially in this case this s is nothing but the eta, right. In this case the spreading rate is equal to eta. So this is actually equal to eta in this case. Okay. All right. So now f of eta is equal to this right. Okay. So in this case, what we're going to do is x, say r half, r is say r half, right, and then this, right. Now, by definition, the mean velocity, right, by definition of the jet velocity itself, right. So, I think so from the question was from the definition of r half, right. The question was right from the definition of r half. So, the definition of r half is that in this definition of f eta, okay, is this definition of eta, right, we are going to add, we are going to use r half in for r, right. So, what we are saying here is the mean velocity, right, at the jet half width, right, over u naught, the centerline velocity. What is this, right? So, we know from our analysis earlier that the mean velocity, right. So, by definition of say jet half width. So, jet half width from definition of that, right, the mean velocity at the jet half width is nothing but half of the centerline velocity. We have derived this earlier, right, that is from definition. So, definition of jet half width, right. So, therefore, this is equal to half, okay. This is equal to half. So, that is f of eta. So, it is given here, the velocity profile is given here, f of eta, okay. So, then f of eta is equal to 1 plus right. So, f of eta is equal to half, which we just calculated, right. So, now let us do the math here and figure out what A is, that is all, okay. So, to do that, I am going to take, yeah, well, okay, or yeah. So, essentially this, or I mean I think I do not need to write this, but what have you, okay, is equal to right. So, now I am going to take square root on both sides. So, therefore, I get this, right. Okay. Okay. Now, if you go here, Okay. So, okay. So, this is something that we wrote here, right. So, eta, right, eta, so we had said this, right. So, eta is r half, right, spreading rate. So, spreading rate is jet half width per unit x, right. So, because x naught is equal to 0, right. So, in this case, so that is eta. So, x minus x 0. So, this is nothing but eta. Okay. So, the eta I am going to write, that is nothing but s, right, the spreading rate. So, therefore, s a s square is equal to root 2 minus 1, right, or a is equal to root 2 minus 1, right, by s square, right. So, so this is what we had to show, right. A is equal to root 2 minus 1 by s square, which is what I did right here. So, A is equal to root 2 minus 1 by s square, that is simple, right. Okay. So, I think that is kind of all that I would like to do. It is very simple, but this is the idea is, so the idea is, if I'm going to just take a minute and sort of look at this, but when we did all this analysis, right, and when we were taking a velocity profile, we were not taking a velocity profile, but we analyzed and realized that the velocity profile, if plotted a certain way, so that velocity profile is for a jet, for a round free jet, that velocity profile is actually self-similar, right. So, now the point is being, putting your engineering thinking cap on. So, essentially start thinking that, oh, okay, so a certain kind of velocity profile is going to be self-similar, right, and it has its advantages. So, what could that possibly be? So, when you write this here, right, is nothing but a simple polynomial, and you write that in terms of the eta, which is a non-dimensional value, variable, right. So, if you do that, so then, so therefore, given any velocity profile, in this case it looks something like this. So, show that how this A could be, right. So, in the sense, if I take that velocity profile, right. So, what this A actually does is that it is giving you actually the relationship or some dependence on the physical nature of that jet. What is that? That is the spreading rate, right, and therefore, we got this here, right. So, that is how the S got incorporated into the whole thing, right. So, S is a spreading rate, right, which is actually giving us a physical feel for this velocity profile. It is not just any random polynomial that we are writing. It's not that. Okay. So, the A will actually give us a measure, right, for the physical feel of the round jet. Okay. All right. So, let us now start with something which is going to be very, very interesting. Okay. So, now we have looked at the physical, we have looked at the physical nature of a turbulent flow, right. Hopefully, you have looked at some of the videos, hopefully, you are getting interested in looking at more videos, hopefully, you are looking around yourself and looking and able to find examples of turbulent flow, right. And you have seen, and I have spoken about this earlier as well, that while we have seen pictures of the surface of oceans, right, and we have also seen a little teacup, or a little smoke from a matchstick, or from from a little muddy puddle, right. So, it could be turbulence doesn't need to be at a very large scale. Turbulence can be at several scales, right? So I think it's time now to sort of quantify those and learn a little more about that, and answer questions in terms of, how is that turbulence? Is that turbulence the same? Is the nature same? The way the energy is being transferred, because there are motions existing. Now, when you have a large scale turbulent flow, so what is going on? I mean, how is the energy being transferred, and what exactly is happening that is turbulent, such a large flow, and then you have a little bit of small little space, and then you have turbulent flow there as well, right? So in the sense, the scale becomes important, right? So let us see, let us see what things we should look at, frankly speaking, right? What things we should look at when you're looking at different scales of a turbulence? What information can we get, right? And besides the fact that this is small and this is large, right? Other than that, what are the similarities, if at all anything, or how different are they, right? I'd like to know. Okay. So I think, what I'm actually starting out now to do is something which is called Kolmogorov Hypothesis. Okay. Right. So let me just jot down what I kind of have said just now, and I've been saying this for a while now. Some of the thoughts really I'm going to jot down. Okay. So turbulence. So let's just say turbulent motions range in size from the characteristic width of the flow right to much smaller scales and how small? Well, they keep becoming smaller with increase in RA, right? So smaller scales with respect to the characteristic length okay. So smaller scales with respect to delta become smaller with increase in the Reynolds number, right? So you see, I hope that you are beginning to see why I started off with a continuum, right? So if I keep saying that, okay, so another point is, so say now that we're looking at, just now we said if this is what could be a possible self-similar velocity profile, right? So we kind of generated that just now. Now, so say I have to create turbulent flow, right? I need to do that. So immediately, the question is, how small do we have to get? Is it that this is something that will happen only at very, if I do this in a very small, small domain, or is it that it can happen on as big domain as possible, right? So clearly, turbulent motions can, be large. I don't think there's any issue with that, right? However, smaller scales with respect to delta. So smaller scales compared to the characteristic length they will become smaller with increase in Re. But the point is, you don't get so small that where you're looking at each molecule separately, right? So that's where your that continuum approach actually comes in. It was important to sort of say that right at the beginning, that we are looking at smaller and smaller scales, right? But we still look at the fluid as a continuum. Okay. All right. Well, turbulence, kinetic energy, and stresses are also important, and they are anisotropic. The Reynolds stresses are anisotropic. Okay. All right. Now, so now let us talk about this for a little while, in the sense that you have a large, turbulent body. You have a body of fluid which is highly turbulent, right? And then now the point. So then you have, you have, say, an ocean, right? And a part of it, right, suddenly starts having turbulent motion. So turbulent motion means random, chaotic, unsteady motion, right? So this is a mechanical phenomena, right? It's a mechanical actual movement of fluid particles, right? So these particles are now moving randomly and very fast and in an unsteady fashion. Now, where suddenly did they get this energy from, right? How is this energy from? And if some particles are turbulent in a very large domain of fluid, some are smaller, right? So what will happen? It will continue to do with this energy like all the time, the same energy. So then they will keep moving around with that same energy. What happens, right? So I think we're going to talk about that. There's something called an energy cascade, right? Energy cannot be produced or destroyed, obviously, right? It can only be sort of redistributed or something, right? But energy as a whole cannot be destroyed or created, for that matter. Okay, so then we come to what is called energy cascade, right? Okay. So now, like I was saying, just try to visualize this picture, right? You have a nice laminar flow going on, right? And then there is some burst of kinetic energy which is added to this flow, right? And they start, vibrating with extra energy, right? And then we have this extra energy, and all this movement, some new movement is happening because of the new infused kinetic energy. So it's unsteady, it is chaotic, it's all over the place, right? Now the question is, when this energy is transferred, right, to say this body of fluid, which is body of fluid, what will it do first? I mean, it will, this energy, so what will it do? Will it go to the particle which is moving around the least, or the particles which are moving in a very certainly larger space, right? So the kinetic energy will be transferred, so transferred to the fluid particles. So which particle will it go first, or what I'm asking is, you have several particles which is making the flow fully turbulent, but as we have seen also earlier, this turbulence is not like uniform, right? Somewhere it is more, somewhere it is less, somewhere things are kind of blurring with each other, right? So these scales are different, right? These motions are happening in different scales. So the point is, when I give that energy, when energy is going to be transferred, where does it transform to first? Does it go to the smaller scales, the larger scales, the medium scales, or is that a concern at all or not? I think that is the question. Okay. Now, it was Richardson, right, who then gives us these clues about that. Okay. So kinetic energy enters the turbulent right, at largest scales motion. Yeah, okay. Now this K, right, what is going on with the K, right, is transferred by inviscid processes right to smaller and further smaller scales. Right. So, this kinetic energy is now transferred by inviscid processes to smaller and smaller scales. Right. So, in the sense that if you have one bulk of kinetic energy, it is going to go enter the turbulent flow and go the whole of it into the larger scales of motion. Right. And then see, these particles are constantly colliding with each other, etc. So, this kinetic energy is obviously it's a mechanical process. So, then this is also going to get transferred. So, from this large scale motion, then it is going to transferred to smaller and smaller scales by inviscid processes. Okay. So, now the energy cannot be created or destroyed. So, then once it goes and then finally when it reaches the smallest scale possible, right, then the energy needs to be again it's extra energy is here, right. What will it do? Well, it gets dissipated. That is the final straw. It gets dissipated by viscous action. Let me write that down first and then we will talk. Finally, the energy is dissipated by viscous action. Okay. Now, so essentially what I am saying is that the kinetic energy enters into the turbulent flow, adds itself basically to the largest scales of motion. Right. It could have dissipated there itself, it does not. Right. It is transferred to smaller and smaller scales, right. And then when it reaches the final smallest scale, right, beyond this you cannot make it smaller, then basically the energy it has been transferred, right, it dissipates, right, it dissipates. So, dissipation occurs at the smallest length scale, right. That is also important to know. Okay, so then now in 1941, right. So, Kolmogorov, so this was an energy cascade theory which was proposed by Richardson, and in 1941, right, this was proposed in 1922 and say a cool 20 years later, right. So, Kolmogorov added further to this right, to the theory of energy cascade by Richardson, right. he added further to this study, and he essentially quantified. That is interesting, right? So the next question can be, oh, okay, so say I have x kilojoules of kinetic energy, which I'm transferring to the turbulent flow. Then how is this going to be transferred? All of this energy is going to go to the largest scales of motion, and then it is going to be transferred till the smallest one. So, I mean, which size will get what sort of energy? Right? So that we would ask that question, and so Kolmogorov actually went and did find the answers. So that's essentially he quantified this whole picture, that you have a kinetic energy, it comes in, it goes and joins with the largest scales of motion, and then the flow then the energy starts transferring to smaller and smaller scales till finally it is dissipated. Okay. So he quantified that. Okay. He also identified the small scales of turbulent. Smaller scales of turbulence. Right. Okay, I don't need to write that. Okay. He also identified the smaller scales of turbulence. Right, because now the point was the kinetic energy is transferred till it reaches the smallest scale. What is the smallest scale? What is the length scale of that? Right, keeping continuum approach, etc. in place. Like we had talked about Knudsen number, right? But this is different, right? We are talking. We are considering continuum values, but this here we are talking about scales of motion, right? Scales of motion, and which essentially define our turbulence. So Kolmogorov quantified these, right? Quantified this, and he also quantified the smallest scales at which the motion in that scale, which actually also called turbulence. Because see, the thought will come to your head, oh, so this is really chaotic. You think of this, especially when you are going out to drive, oh, drive slow, go slow, because if you go slow, all problems will be solved. We tend to think that. So the point is that you have very large scales of motion is happening. So does that mean that if I slow it down, right? If I slow it down, if I slow the motion down, then the transfer of energy, what will happen to that, right? And if I do that, then how small can I get, so that after this, even if you transfer more energy, right, you will not get any more turbulence. So another way to look at that is that you've seen the pictures of turbulent flow. So you have large large volumes of turbulent flow, then you have smaller ones and various ones, etc., right? But when we are not, however, looking at a single particles, this is still a continuum. I'm looking at the fluid as a continuum, right? So say I want to stir. Say I want to stir again, sugar in a teacup, right? So I need a minimum amount of turbulence. I need a minimum amount of turbulent flow so that the mixing can happen, right? So what is that minimum scale of turbulence that you need, right, to do that? So this is looking at it in a positive way, right? So in the sense that how much energy will actually incite some kind of turbulence. So to do that, the minimum amount of energy that is required to even produce a little bit of the smallest scale of turbulence is what was identified by Kolmogorov, right? So in 1941, so he actually took the propositions of Richardson, which he made some 20 years back, right, the energy cascade, and he put some numbers into that. right. So, essentially that is what he did. So, therefore, we have the Kolmogorov scales, they have his name on it. So, that is why. Okay. All right. So, I think we should be able to do this before we close. Okay. Okay. So, now let us do this. We consider a fully turbulent flow. Okay, at high RE. Okay. So, characteristic velocity this, then characteristic length that, right. So, therefore, right, the Reynolds number is large. Okay. Again, this is from Richardson. Okay. Now, turbulence consists of eddies, right, of different sizes. Eddies of different sizes. Okay. So, again for this he suggested let the characteristic length be L, right, characteristic velocity. Okay, we are going to write that. Let us just say it is that, right. Therefore, characteristic time scale. Okay, is equal to L by U. Yeah, okay. Now, when I say eddy, you've heard the name earlier, right. When I say eddy, right, what do I understand? What do I understand by saying eddy, right? So, turbulent motion localized within a region L. Okay. Now, eddies of the largest size, let us just say. That could be interesting, right? How big a turbulent flow can you get, right? So, will it sustain itself, right? Can it sustain itself? So, eddies of the largest size, okay. So, characteristic length is that, okay, and characteristic velocity is this. Okay, I keep writing that. Well, we can write that, but let us not do that. Right. So, essentially I wrote the velocity to be this. So, now I am writing the length to be L naught, so then corresponding value of this is the velocity, right. So, you see I have a fully turbulent flow, right, and there the characteristic velocity is given by superscripts plus, right. I have Richardson's eddies, I mean the proposition where he says characteristic length of an eddy is a turbulent flow, right. It consists of various eddies. So, characteristic length, he says small case L, velocity is a function of that, and the time scale is this, right. Now, eddy is essentially turbulent motion localized with a region L, right. If I take turbulent flow, and just sort of hold it up in a small little place, then it becomes an eddy. Now, then the small is how small, right. When I say small, when I say big, so how small, how big, what is the reference frame. So, eddies of the largest size are, so characteristic length, let us just say is L naught, and characteristic velocity is this. Okay. So, let me just write this, and we shall sort of discuss this in the next class. Okay. L naught, right, which is essentially the characteristic length of an eddy, right, is comparable to this L plus, right. L naught is actually comparable to L plus, right. Then the velocity is of the order of turbulent intensity. Right, that is okay, let us just sort of is equal to this. Okay. So, we will discuss this further in the next class, and then of course, we will get into more details of this. Okay. I will stop for now. See you in the next class. Thank you.